In this video, I'm going to show you something called a helium dilution refrigerator. Now, what that is something that achieves cooling by taking advantage of the physical properties of different isotopes of helium, specifically by mixing them together. The two relevant isotopes are helium-3 and helium-4, and the fact that you can cool by mixing them depends on the fact that when you cool a mixture of them to a really low temperature, the liquid blend actually separates into two components, a helium-3 pore component, which is dense and settles on the bottom, and a helium-3 rich component, which is less dense and sits on top. Then you can stick a pipe down into the helium-3 pore phase and start vacuuming helium-3 out. This throws the system out of equilibrium, and as a result, helium-3 moves down from the rich component into the pore component, and the dissolution into the pore component has a mixing entropy associated with it and a cooling effect. The helium-3 rich gas that's vacuumed off is fed back into the rich component on top to keep its helium-3 concentration high. Here follows the footage of the actual dilution refrigerator. This thing is a 25 microwatt helium dilution refrigerator. It's not in its dewar. These fins are for thermal shielding. So that is the mixing chamber there. It's connected by a copper cold finger down to the sample mount there. These little clips here at the end of this cold finger are electrical connections, and you plug those onto leads on the sample holder. So that's the actual sample holder, and those labeled connections at the end of the cold finger connect to those leads sticking out of the bottom of that copper square. And the actual sample is usually varnished on the center of that copper square, and the leads are connected to the sample, and those little metallic spots in rows all around, and they connect to those leads that the connectors in the cold finger connect to, and you screw it on the end of the cold finger. Then that's a heat exchanger. The heat exchanger pulls heat out of the gas that's going into the mixing chamber, and it does this by conducting the heat into the gas that's leaving the mixing chamber. This is the dewar that it's operated in. It goes into the floor. It turns out that you actually have to take the refrigerator itself out of the dewar every time you want to load a new sample, and then you load the refrigerator back in the dewar here to actually run the refrigerator and do your experiment. That propane tank there contains extra helium-3, helium-4 mixture. And that's a liquid nitrogen dewar and an associated cold trap that's part of the helium-3, helium-4 mix system. Then over here there's another cold trap that goes into the main bath. So it's a liquid helium cold trap, and that's also part of the helium-3, helium-4 mix system. The gauge there is actually measuring the pressure of the helium bath that cools the magnet, because there's a magnet in there so that they can expose the samples that are being measured to a magnetic field. This vacuums the 1K pots, and then this actually vacuums the helium-3, helium-4 mixture, so that's mostly pulling helium-3 off out of the dilute phase. And it's precisely that causes the cooling, because when you pull helium-3, the more volatile isotope, out of that dilute phase, it's out of equilibrium, and helium-3 moves from the concentrated phase into the dilute phase, and that mixing of the helium-3 into the dilute phase is what causes the cooling, and that's what's going on in the mixing chamber. This helium-3, helium-4 vacuum line that I showed you actually goes up with a bunch of other vacuum lines to the ceiling there, and then across through the wall to vacuum pumps that are in the room over there. So it's actually kind of a large system. The box there on top controls the helium-3, helium-4 system, so that's what you use to control where the gas is and how it's flowing. And then this box down there controls just the pure helium-4 system. Okay, you've seen the dilution refrigerator. Hopefully my explanation at the beginning of how one works makes some sense. Hopefully you learned something interesting and enjoyed the sights you saw in this video. If you did, please give it a thumbs up and don't forget to subscribe. Dietrich out.